Welcome back, everyone. In today's lesson, I will teach you the three equations DSGE model and we'll work through the dynamic response to a monetary innovation shock. I'll derive the trial solutions and then we'll solve for the coefficients step by step. So let's begin. Suppose we have an economy which is described by the IS curve, the Phillips curve, and the Taylor rule. And we want to see the impact of a monetary innovation shock using the methods of undetermined coefficients. Okay, to start, I'm firstly going to assume a few things for, let's say, simplicity. So I'm going to assume that there is no growth in innovation. So I'm assuming the value of AT is equals to 0. And by the way, these are all log values. So when I say ln A is equals to a 0, where ln A is basically just a small a, doesn't mean that the value of technology is 0. It just means that because we know ln1 is equals to a 0, right? So technology is not actually 0. It's just normalized to value 1. So the value of technology is normalized to 1. It's not a 0 anyhow. So we assume there is no productivity shock, and we can assume that there is no inflation shock. So mu inflation T is equals to 0. We can assume that there is no shock to output either. And this kind of makes the model much easier to work with. We can also actually assume that there is no government spending, because that's also yeah, let's assume that there is no government change in government spending. Okay, with these assumptions, our model collapses to, I'm going to copy this down, drag it down, and let's see. This becomes, where does, okay, since G is equals to, all this disappears, the output shock disappears, this goes away, the inflation shock goes away, this stays, yeah, and that's it. This is the model after we've imposed the assumption of no growth in technology and no growth in government spending, and there not being any shock in inflation and output. Okay, so this is a simplified version. This is equation 1. This is equation 2. And this is equation 3. So in this case, we have 3 endogenous variables, which are output, inflation, and the interest rate. This can be potentially very difficult for us to solve, because if I put this in matrix form, it's going to give me a 3 by 3 matrix, right? So that's just going to be a lot more difficult for us to solve. So what we can do is we can just convert all of this into a 2 by 2 system by putting equation 3 in 1. So substitute equation 3 into 1 in order to obtain a 2 by 2 system. And 2 by 2 system is going to be much easier for us to manage. Okay, so let's do that. This is the first and the second equation. The second equation actually remains the same, so I'm just going to take this and I want to substitute the value of I. So this is how it's going to change. This is what I wanted to change, right? This is the value of I, and I'm just going to substitute the Taylor rule over here. The Taylor rule says that you should increase the nominal interest rate when output deviates from its natural levels, and increase the interest rate when inflation increases beyond its expectations. Okay, so now that we've done this, now you have a more simpler system to solve. Let me write this one again down as well. Okay, so we start off first by identifying the endogenous and exogenous variables. Okay, so this is the most important thing. So my endogenous variables in this system is output and inflation, and the shock that is being created is a shock to the monetary policy. Like there's a shock in the money market to the interest rate. So this is going to follow an AR1 process. So whatever is subject to a shock, always, even if you plug this data into MATLAB and Linear, you will have to convert the shock variable into an AR1 process. Okay, so since this is the shock, I'm going to write it down as a AR1 process, t minus 1 plus epsilon, and this is just white noise. It's normally distributed with mean 0, variance 1. Okay, so what are the trial solutions? The trial solutions are based on our endogenous variables. So the first trial solution is going to be A, U, I, T, and this basically tells me the multiplier, because it tells me how output changes after a shock to monetary policy. So it tells us the money multiplier, the impact for instance a monetary contraction can have on output. So for instance, I could expect that when there is a positive shock to the interest rate, which means that the interest rate is rising, the central bank will have to reduce the money supply, because then there's an excess supply of money being created in the money market, and this basically should shift the LM curve to the left. And once the LM curve shifts to the left, there is going to be a fall in output. So I do expect that there's going to be a negative relationship between output and this shock. So I expect the value of A to be negative. Okay, the next trial solution is going to be, what was the next endogenous variable? Inflation. And we can say that we can put a constant C here and see the relationship. Okay, so the change in inflation after a change in the interest rate is basically C. And I know that when the LM shifts left, I am going to expect a fall in the prices, right? So the inflation level should fall. So I do expect that my expectation is that A and C are negative. Okay, so now that we've found these trial solutions, I need to substitute these trial solutions into equation 1 and 2. But as you can see, I have like yt and inflation t here, but I have expected value of future inflation and future output. I need to find that over as well. So let's do that. If yt is equals to a u I t, then that would mean that yt plus 1 will be equals to a u I t plus 1. And since this is a AR1 process, this is going to be u I t plus epsilon t. Okay, so we have an a rho u I t plus a epsilon t. So if I take the expected value at time t of yt plus 1, since this is in the same time, so therefore there's like you expect the value that you see right now, so there's no expectation sign here, and the expected value of epsilon is actually 0, so that's what you get. Similarly, I don't need to do the whole procedure again for inflation, but if you follow the same logic as above, you'll get that if you take the expected value at time t of inflation t plus 1, then you'll get a c rho u I t. So okay, now we're going to substitute all of this information, basically which information? This, and this into our two equations. So let's begin. So far so good. I hope this doesn't look scary. I've tried to simplify this concept as much as I could. Okay, so let's put the value of y. Y was an a u I t. This was an a rho u I t minus gamma over what was the symbol? I think sigma. This I don't know what's it called. Okay, yt was a u I t plus coefficient of inflation and c u I t plus uid remains there minus there's an expected sign here, so what was it? C, yeah, c rho u I t. Okay, as you can see, the error ut, the shock, appears everywhere, so we can cancel this out because you can take it out as common on both sides and it'll just disappear. Okay, so what do we have? We have an a is equals to a rho minus delta sigma coefficient of output a minus gamma sigma coefficient of inflation c minus gamma over sigma and then plus gamma c rho over sigma. Okay, remember we are interested in finding the multipliers, so I want to make form a matrix in which I can find the values of a and c. So I'm going to take the a and c on the left side. So what do I have? I have an a minus a rho plus gamma delta sigma coefficient of output. Yeah, this all comes with a. So I'm just gonna take like a outside, so this becomes a 1, that stays a rho, and a is outside. But I hope I don't make any silly mistakes because that is gonna be really embarrassing. Okay, gamma and sigma coefficient of inflation c. Okay, so I have everything on the left hand side. This is the coefficient now for c, and we have a constant gamma over sigma, and this is going to be C rho minus 1. We can also, if we want to tidy this up, I can even write it like this: gamma sigma power minus 1. So I can avoid like a fraction by writing it like this. I have seen some texts you do it like this, so I guess it's fine. Gamma power 1 C rho. So this way we can avoid a fraction. Okay, so this is the first equation, and let's now put the trial solution into the second equation. Hopefully that will be less torturing. Okay. I feel like I need to apologize for this being ridiculously long, although it's not my fault. I didn't create this. I'm just the messenger. Don't kill the messenger, please. Okay, so inflation. Okay, let's substitute the trial solution C and U, I, T, and this wiggly cross sign, and C rho U I T plus whatever the symbol is. I probably should start memorizing what these symbols are, but I'm just so lazy. Or maybe I'm not lazy. I shouldn't say bad things about me to myself. I'm not lazy, I'm just busy. Okay, everything on the left side. Okay, so I have just this with A plus C, a cross and a row minus a 1 with C, and there's actually no constant here. Looks kind of strange, but it's okay. This is our second equation. Okay, so now we can actually convert this into matrix form. Let's do it. I have a 1 minus rho plus gamma, the inverse of sigma, coefficient of output, right? And then I have a gamma inverse of the sigma, and inflation. Did I write it right? Yeah. A and C. Did I get it right? Did I get it right? I think I'm forgetting something. Oh God, there's a C here. So C should have, oops, let's fix this. Yeah, why didn't I? I just noticed because I was about to write this on the side. Okay, let me fix it. Apologies. This C should actually not be here. So on this side, I should only have a minus this gamma over delta. And when the C goes there, yeah, so there's going to be a row here. Yeah, now this looks better. Yeah, C is here. I hope I didn't mess this up this time. Okay, this goes on that side, becomes a positive. This will become a negative. Yeah, I think I've got it right this time. Okay. I'm so glad I caught this mistake right now, otherwise I would have been in trouble later on. The multipliers would have just been totally wrong. Okay, gamma inverse of delta and coefficient of inflation minus a rho, and over here my constant is where is it, gamma inverse of delta where is it? I just fixed it. Yeah, over here. There it is. And there's a negative sign here. Oh, I forgot to bring this down. Let me bring this down. Yeah, this is the fixed version. Okay, so this is fine. I just need a negative sign here. Okay, perfect. I hope this is correct. Okay, the next equation, the coefficient of A is this. C is x rho, it looks like a P, minus 1. And there's a 0 here actually. Okay, so now we can either use the Kramer's rule, or we can actually just find the inverse of this matrix and multiply it over there. So it's your choice. I usually actually prefer the Kramer's rule because I'm very comfortable with it. But there's no growth, right? Unless you put yourself in a lot of discomfort. So let's just do the uncomfortable option, which is taking the inverse. I hate it. So let's do it. This is the matrix. It is a 2 by 2 matrix, so I shouldn't feel scared of taking the inverse. I don't know why it bothers me. Okay, 1 over the determinant, which would be a 1 minus rho plus gamma inverse of sigma, coefficient of output, being multiplied by x rho minus a 1, and then minus, so we've multiplied these. I'm going to minus the product of these two. So minus this into that. Okay, so this is the determinant. And now I'm going to this is so big. I'm going to kind of make it smaller. Okay, these switch. And these just change their signs. So I'll just keep the gamma here. I'll just put rho minus inflation coefficient. Okay, so far so good. Let's close this. Okay, so the answer to A and C is, if I take this inverse, and unfortunately I'll have to like make this a bit tiny, so because I'm running out of space, and I need to multiply it by this column. So that was a minus gamma inverse of sigma into a 0, right? And now let's do matrix multiplication. This comes as it is, and we have a x rho minus 1 into a gamma, and there's a negative sign, so I'll have to let's just invert this. Actually, I can incorporate the negative sign here, and this becomes a 0, so that's easy. Then we have this. Okay, so the value of A. So the value of A is 1 minus x p rho, multiplied by gamma, this, over this whole expression. Okay, so the numerator, in fact, right now is a positive number because these are all constants. These are small numbers and they are going to be less than 1. So this is a positive number. This right here, this expression is positive. This is positive. I'll just write, this is a positive expression, this is positive. This is also positive. I'm not sure about this one though. Okay, let's just do a question mark. It could be negative, it could be positive. This is a positive, this is negative. Okay, so the denominator actually seems like we have a positive numerator, but we have a negative number minus a negative number, especially if the coefficient of inflation is greater than rho. Okay, so that would give us a value of a which is less than 0. So remember, we require for this to work x into rho is actually less than 1, and gamma and delta and the coefficient of output, and what else? I can see a rho, rho. All these values lie between 0 and 1, and we need the coefficient of inflation being greater than rho. So that's when this works. Okay, moving on to C. C is equals to, oh, that's going to be easier. This. So the numerator is again a positive number, whereas the denominator is a negative number. So therefore the value of C is going to be, it's going to be negative. We need this to be positive. So we're going to have a situation where the value of C is negative if and only if. For this to work, all these constants are, what else? Inflation, output, coefficient, all of them are less than 1 and greater than 0. This kind of looks bad. I'm just going to reduce the size so I can write it in a row. So all of these are greater than 0 and less than 1. Okay, so this shows that since the value of A and C is less than, let's just first focus on A, is less than 0, thus a monetary innovation shock causes a decrease, a fall in output. Similarly, since C is negative, thus a monetary innovation shock causes a fall in inflation. And what about the overall impact on the interest rate? So let's see what happens to the interest rate. Remember, the interest rate was given by this equation, and let's see what happens here. I want to see what happens to the interest rate. So I want to take the derivative of the interest rate, right, with respect to the shock variable. Okay, so I'm going to get the change in output with respect to the shock variable, and then I'm going to get the derivative of inflation with respect to the shock variable, and this obviously becomes a 1. So this is multiplied by A, and this is multiplied by a C, and these are actually negative numbers, and this is a positive number. So the result is kind of ambiguous because this is a negative number. So for instance, if this expression C is let's suppose it's a greater than 1 in absolute values. Let's suppose it's a -2, right? And this is a 1. So it's going to be, so if it's greater in absolute values as compared to 1, then you're going to have a fall in the interest rate. However, if it's actually some value which is negative but not greater than 1, so for instance a -0.5 plus a 1, so in absolute values it's less than 1, so the overall answer is going to be positive, which would mean that the interest rate actually rises. So our impact on interest rate just depends on what values this takes. Anyhow, you can also actually show this diagrammatically, because we know that when I won't make a diagram right now because I don't want the lesson to be too long, but we know that if there is a positive, if the interest rate increases, there is actually an excess supply of money in the money market, and therefore this has to be eliminated with a monetary contraction, and a monetary contraction therefore shifts the LM to the left, and we know LM shifting to the left actually would increase the interest rate, right? But we also know at the same time that when the money supply falls, and this brings about a rise in the interest rate actually makes it very hard for people to fund their investment, because they have to pay back more on loans. So when when the investment level falls, the IS curve would shift to the left as well. And this actually calls this a fall in the interest rate. So you can see like the overall impact actually depends on how much each of these curves shifted. If they exactly outweigh each other, then there will be no change in the interest rate, right? Which would mean actually that the value of this would actually just be exactly equals to a -1, and there would be no change in the interest rate. If the LM impact outweighs, then overall there's going to be a rise in the interest rate, and if the IS dominates, then there's going to be a fall in the interest rate. But the key takeaway is that don't think that if there's a positive shock to the interest rate, then in the whole economy the interest rate is going to rise. The impact on the interest rate is still ambiguous. Anyhow, so that's just a full solution. I derived the coefficients, interpreted the effects of the shock, and we connected the maths to the economic intuition. And just go over your steps once more, and it will become very easy with practice. And in the next two parts, I will solve for a government shock to government spending, and then a shock to technology, and then you'll completely absorb the procedure, and you'll be able to manage any kind of shock then. So I'm just going to show three kinds of shock in these lectures, and you'll understand how to replicate it to any kind of shock which is given in a question. So that's it for today. Take care. Have a good day.